Okay, hi everyone. So today we're going to look at the last two concepts in our wave chapter. So over here you don't see my face, but but you just bear with my sound, okay? Just listen. So over here, let's fill in the blanks for this wave topic. We're in page number 8. Page number 8. And we are going to go to the next concept called the wavefront. Okay, so what is a wavefront? Okay, a wavefront is an imaginary line. Okay, it is an imaginary line, okay, and it joins all the adjacent points that are in phase, right? Join all. So what does it mean? It is joining all the crests together, all the troughs together, and all the other lines. So I think usually what we do is we will draw for the crests. Okay, so all these imaginary lines over here, we will draw all for the crest. For example, if you see over here, this one over here, this one, all these are crests. So this imaginary line is a wavefront. Okay. Now, in the same way over here, we have, for example, in the same way we have another wave like this. Okay, moving outwards, we have another wave like this. All right. So these points are our crests. Right, they are our crests. Okay, so these lines, these circular patterns are our wavefront. So as you can see, a straight dipper will produce a plain wavefront or a straight wavefront, whereas a spherical dipper will produce a circular wavefront. Okay, so what are wavefronts again? Is an imaginary line joining all the adjacent points that are in phase, or more like joining all the crests together. So the second way to write this is an imaginary line on a wave that joins all the crests together. Okay, so this is the second way to write this. Now, and then the thing is that we can make use of these wavefronts to tell us the wavelengths. So for example, this length over here would be one wavelength. Okay, another one is this length over here. If you notice this length over here, right, or even this length over here, or even this length over here, even though they may not look the same, but because it's a 2D for a 3D thing. Okay, so all these things are actually your wavelength. So this is one wavelength. So two wavefronts apart will give you one wavelength. Okay, so with this in mind, let's take a look at this question over here. A wave generator which makes 5 oscillations a second, okay, is used to produce waves in a ripple tank. So which of these is the correct for the wave produced? Okay, so let's analyze this one first. 5 oscillations per second. So what does this mean is that the frequency is 5 every second. So 5 hertz. Okay, so the frequency is 5 hertz. So the other two is wrong. Okay, next one, let's take a look at the wavelength. Now over here, we can take a look at this wave. Just nice, we have 5 wavefronts. I'm looking for this wavelength, like the two crests, distance between two crests. Okay, so how many wavelengths are there? 4 wavelengths is equals to 12 cm. So 1 wavelength is equals to 3 cm. So answer is, like you can say that the answer is B already, but just to double check, V equals to F lambda, 5 times 3 is 15. So answer is B. Okay, so this is for practice G. Now, the very last concept over here is something that is not really tested, but it will be good to know, just in case people decide to be a bit creative. So what is going on here is, here we are going to talk about the refraction of waves. So what are the refraction of waves is when waves go through a shallower water, okay, the ripples will slow down. Okay, the wave will slow down, and you can see the wave actually nearer. So where do you see this happening? On beaches. Okay, on beaches where things far away, you may see further wavefronts, but closer to the beach, you can see that the waves are actually more frequent because the parts are actually more shallower and your waves are traveling slower, so you get more wavefronts. Okay, so wavelength becomes shorter because the speed drops. Okay, so the frequency is fixed by source. So the frequency is fixed. This is very important. So since v equals to f lambda, the wave becomes slower. Okay, so the thing is, when waves travel from a deep to a shallower region, they slow down. As a result of this slowing down, there's a change in direction. This is known as a refraction. Okay, so regarding refraction, right, let's take a look at analyze this a little bit. Let's take a look at the wave formula for this one over here. Okay, so we have v equals to f lambda. Now, under refraction, this one would be the same. Okay, and then as the wave travels in shallower water, the wavelength decrease, and because of that, the speed also decrease, because directly proportional. Now, so this is the first thing that you need to realize for the whole situation, is that the frequency will be the same. Now, next is when there are two phases, when you have a shallower and a deeper part. Now, let's rearrange this thing to make it become f equals to v over lambda. Now, so because f1 is equals to f2 for this case, okay, so v1 over lambda 1 is equals to v2 over lambda 2. Okay, based on this formula over here. So we can make use of this to do a little bit more analysis in the second part. Okay, so let's take a look at the example over here. Okay, so a plane wave in a ripple tank undergoes refraction. Initially, the wave has a wavelength, so the initial wavelength, initial speed. After refraction, we have a final wavelength, and we are looking for the final speed. So this one over here, this one is actually look in your refracted wavelength. Okay, so this one is shallower, this one is deeper. Okay, shallower have shorter wavelength. Now, so because f1 is equals to f2, okay, so your v1 over lambda 1 based on the formula is equals to v2 over lambda 2. Okay, so how do we do this? We just sub in lor. So v1 0.20, lambda 1 would be 3 cm, v2 is 1, v2 I don't know, then lambda 2 would be 1.5 cm. So take note, yeah, even though it's not in SI unit, you need to make sure that these two units must match. Okay, so with this one, we can solve for v2. v2 will be equals to 0.10 meters per second. So the answer is A. Right, so and this is a good place to stop. Right, bye.